All right, let's get started. So lots to go through today. We're going to work on Bomb Lab together. Shall we get started? Okay, so first some announcements, right? Bomb Lab, programming assignment 4. This is the famous assignment from CS211. It's an assignment that comes from the textbook. It is out and it is live. So right now it's stated to be due April 5th, a Tuesday. And all the due dates for the rest of the semester are up to date on the class syllabus, so you can always check that out here. So we've got 3 more programming assignments due, all spaced out in 2-week intervals as before. The due dates have been slightly adjusted, so Bomb Lab was pushed back, and so everything is pushed back by a couple days. You can find the up-to-date syllabus over here. We'll do a routine short quiz next week, so that will be short quiz number 6. We're on track to having more short quizzes than planned, so right now it's the system set up to drop your lowest short quiz grade out of the ones that we offer. So same thing, right? So next Tuesday to Thursday, March 29th to March 31st, we'll do a 30-minute short quiz, 2 tries, and so forth. It'll be about the topics that we talked about just before break and today and on Thursday. So just charting a plan going forward, right? So if you're reading and following along the textbook, you should be up through chapter 3.5, which is about how arithmetic operations are done in assembly. Today we'll do a Bomb Lab demo, so we'll demo and walk through how to get your environment set up to do programming assignment 4. And then Thursday through Thursday next week, we'll cover chapters in the book that help you crack different parts of the Bomb Lab. Okay, any questions about the general strategy? So let's get started, right? Programming assignment 4, defusing a binary bomb. So the goal of this assignment is to train you to use a debugger, such as GDB, right? So this is the long-term real impact of this assignment. And along the way, there's a few things that it showcases, which is you'll see how assembly instructions realize a program, right? How a program runs as assembly instructions. This is a task in reverse engineering and debugging, right? So if you're going down this trajectory of computer science where you really like computer architecture and this kind of topic, you like this hardware-software interface, well, this kind of task that the Bomb Lab demonstrates, reverse engineering, and given something that's opaque and difficult to pick out, figuring out what's inside it and how to work around it. This is a typical task for something like in security or in networks, right? So you can pretend that this bomb that we're giving you is not like a class assignment, but if instead it's some kind of piece of malware or a virus or some kind of network bug, right? This kind of debugging and reverse engineering skills is really valuable for doing work in that direction. So how to get started, right? So the most basic way to get started is to go to the assignment description on Canvas. Okay, so let's go to Canvas. This is the programming assignment 4 on Canvas. To get started, well, everything is in the PDF here. And in the PDF here, the first step, right, you'll want to read through this in detail, but we're kind of going to go through the major highlights to get you started here. The most important part is to go to this website here, atlas.csrutgers.edu. The port number, right? So this is a port number on this machine. You go to this physical machine called atlas.cs.edu, rutgers.edu. And at this port right now, it's hosting a website. right? And it's finicky. If we have a lot of people trying to access it all at once, it's going to not be able to service all the requests. I suspect since a lot of people are following on right now, there's a lot of requests to do this. If you get like access denied, one thing you can do is try privacy mode in your browser or switch to a different browser to try to download it, or just wait a few minutes to try to get to the website. I expected this because I just imagine there's a lot of people following along right now, and so I'm not going to be able to access it. Here you go. So finally, it's given me access in. You'll want to download your bomb lab package, your PA4 package, enter your uni and your NetID and your email address. This is important, right? So you don't want to do this on behalf of somebody else, right? So it's important to enter your real NetID here because this is how we associate the grade that you get on bomb lab with your grade in the class for this assignment. If you submit this info, hopefully it'll give you a bomb to download right away. And right now, as I said, it's very finicky. If it were working fine, you'll then download a bomb package. So here we go. Finally, the server serviced our request, bomb 142 just downloaded. If this is really, really crashed out, go to Piazza. So one of the TAs, Arihant, he's doing yeoman's duty of keeping this system alive right now. And so if it really is not responding, then Arihant will go and restart the bomb lab server on Atlas. Okay, any questions up to this point? Right, so hopefully some of you have already tried, right? Given the fact that this number is all the way up to 142, I'm guessing that some of you have already attempted through this step. Okay, so this bomb lab package, right? You need to run it on the iLab servers. So this package just downloaded to my desktop. And in order to move it to iLab, you've got a couple ways, right? This is just like moving any other files back and forth between your laptop and iLab, right? You could use something like CyberDuck, or you can use secure copy. So if you're just going to use SCP, secure copy, from local computer to iLab, the command would be SCP bomblab 142 is the package I downloaded. And then the destination is the second argument. So destination is your NetID at ilab.cs.rutgers.edu, and then followed by the path, followed by where in your iLab account this file should go to. Right? So the directory here would be tilde, indicates your home directory, where all of your files are stored on iLab, and subdirectories in there, wherever you feel like it's sensible to put it. Right? So the downside of doing this is you don't have tab completion, so you kind of have to know your way around the destination computer by heart. And if you don't like doing this, CyberDuck is always a very nice graphical way of moving files back and forth. Right? So if I enter that, it's going to usually ask me to log in. I'm already logged in, so it's not asking for my password. And then it transmits the tar file up over to my directory on iLab. Okay, so here, as you see, now I'm in iLab in this tab here. In my 2022 2.11 directory, I now have bomb142.tar ready to go. So any questions up to this point? Let's keep following along in the assignment description on what it wants us to do. Right, so now that you've downloaded the tar file, moved it to iLab, you'll want to untar this directory, this tarball. And so the command to do that is tar tar.xvf and the tarball name. And that will unpack the tar file into your directory here. Right, so inside this tarball, there's a few files. One is the README file. Yeah. So if you download it from the Atlas website here, atlas.cs.rutgers.edu, if you're just using your laptop, this tarball is just going to go to your local desktop on your laptop. Right? You can put it wherever is sensible to you, right? If you want to keep things organized, it probably should be somewhere in your PA4 directory. So in this directory now, we have some files. So one is a README file, and this is important, right? You don't want to be solving somebody else's bomb. Each of these packages is uniquely identified with your uni or your net ID, and this is how the grade is going to be associated with your class grade on this assignment. There's a few more clues here, right? So it seems like it gives us a source file, a .c file, which is really just a top-level C file for the bomb program, right? You can run this bomb, or you can see that you can read through this file, and it just gives you a kind of high-level outline of what goes on, right? So there's some features here that I'll point out. It seems like it's generally organized in multiple phases. So there's phase 1, phase 2, phase 3, and it's just running through these different functions. After it runs each phase, like here after phase 2, it seems like it says, okay, there's a function that's called phase diffused, right? Given that this is a bomb, diffusing sounds like a good thing that you diffuse that phase. And it seems like as you go through all these phases, once you diffuse all the sections, that seems like your goal, right? So the question now is, what does it mean to diffuse this bomb? Okay, what other clues are there, right? So another clue is we have this bomb, this file here. It's executable, right? It has the flag X here, meaning that you can run this program. So let's go ahead and run it. Okay, so we're now running this program. You downloaded this. This was compiled to run on x86 machines. You can run it on iLab. And so it seems like it wants some kind of input. So I'll say hello. And I just typed in hello with a W, and it goes boom. It's blown up. Right. So another feature of this programming assignment is there is a live scoreboard also on the Atlas machine, where the progress of each bomb through how many phases have been diffused is tracked live. So these are all classmates in this class here. And my bomb 142, has just blown up with one explosion here. And right now its score is 0. If you detonate your bomb too many times, don't worry, just download another bomb, right? So this is a learning process. Once you figure out how to crack this assignment, you can download a fresh bomb, and your last score will be the score that you get on this assignment. Okay, so any questions about what's going on so far? Does everybody know generally what's the idea
that you got on this assignment? Do you mean like the score that we got on the latest bomb that we diffused?
Yeah, so somebody on voice, you want to ask the question again?
Yeah, so what did you mean by the latest bomb will be the score that you get? Does that mean that if you, let's say, get a bomb and then blow it up and then get a different bomb and then you diffuse all of it correctly, that score will be kept and not the one that blew up?
That's right. So the last the last bomb that you download and you crack will be the score that's reflected for your course grade. And there's no penalty for downloading additional bombs, right? So you wouldn't want to be doing this too often. In fact, today we'll show you exactly how to not set off your bomb while running through it. But there's no penalty if you mess up one too much. Just get a fresh one and keep trying. Okay, so one critical thing here is don't wait until the last moment to try to get these bombs. The Atlas server would crash if hundreds of people are trying to start the assignment at the same time. So with any programming assignment, starting early is critical here. Okay, so let's go through our description and see what else it has us do. Right? So we just introduced what are the various parts of the assignment. You'll need to run this on the iLab machines. If you run it on any other machine, if you try to run it on your laptop, it will count as an error. And in fact, it may cause the bomb to send a score to the scoreboard that says you tried to run it on some machine that's not iLab. There's some logistics about how the score is tracked here. And here it suggests that you can in fact run your bomb, /bomb, run the bomb program, and you could give it some text file. And it seems like this text file should store a solution that allows you to crack this assignment, right? So there will be some file, say my solution on txt, and in here we would store our solution, which is obviously not just hello, and you can run your bomb with my solution as the input. And the bomb will read that solution file and see if that's a correct set of solutions. And if it's not, it blows up and you get more points knocked off. Right, so if we refresh here, bomb 142 has now, well, it's soon going to blow up some more times, but it'll keep track that it's blown up. Okay, so this talks about the scoreboard. There are various hints here. So there's a bunch of resources that we posted on the class canvas and also in today's slide that will give you pointers on kind of what tools to use, what commands to run to try cracking this. So definitely read through all of this. This is not in a format that's easy to explain in the class format here. So this is kind of reading for in your own time for your own sake. Okay, very good. So what we'll do now is we'll switch over to my course notes for today, and we'll keep walking through what things I want to show you here. So we've set this up. You've downloaded the bomb. I've shown you the web interface for tracking the bomb progress. We've unpacked the bomb. In fact, we've run it a couple times now. It's blown up. And here we're walking through what's in the package. You have the skeleton, high-level kind of structural code showing what goes on in the bomb program. You have the actual program here. And notice how this program obviously is doing a lot more than what's shown in bomb.c. Right? Bomb.c links in some other header files, some other .c files to implement the functions inside it, like things like phase one. That implementation is hidden from you. You don't have the source file for how phase one is actually coded up. There's a few things that will provide useful information here. Right? So we'll walk through these pieces of useful information next. The basic idea here is you're given this bomb program, right? Bomb is a binary file. We can, in fact, take a look at it. I can use less, which reads just files, opens it up, and we can try to see what are the contents of the file. The less program here, it says, bomb looks like a binary file. Do you really want to read it? And I say, sure, go ahead. Right? So it prints out all this gibberish. Why is it printing out this gibberish? Yeah, so none of this is text, right? So remember how we had a program that's printed out ASCII characters, and a bunch of the numbers inside a single byte don't encode any characters, right? So you can chop up this file into bytes and bytes and bytes, and many of those bytes don't correspond to printable characters. And so now that we're trying to read this file and just print it out as text, it's showing, okay, most of this content, it's not text, right? There are some pieces of clarity here. Okay, it seems like here there are some strings, some human readable text, right? There's some other gobbledygook in here. But for the most part, it's a binary file, and its meaning is obscured to us, right? So one thing we can do is this command called strings, right? So what does strings do? We can look at the manual for strings, and it says it takes a file and it prints the sequences of printable characters, right? So it'll take a file and it'll open it up, and it parses through this binary file and says, okay, maybe there's some human readable text in here. Go ahead and print out the human readable text. And so we can do that, right? So let's say strings bomb. So this will open the BOM file and read through it, throw out the characters that are not printable, and extract the ones that seem to be human readable, right? So if you opened up the BOM file, there's all of these words, text strings in here that are inside the BOM file, right? So there's some stuff that you want to study here. They're like passwords, maybe, various other strings, right? All of this may provide useful clues on how to crack the BOM, right? Obviously, somehow, some of your solution will be hidden somewhere in this file, some pieces of it, right? If the solution is some string, you'll find the solution here, if it's just comparing two strings. There's some other strings here, right? So it seems like the rule that it must run on iLab is encoded in here somewhere. So in the file, there's the program knows about these computer names, iLab 1, 2, 3, 4, so forth. There's a bunch of other things, right? So the printouts are here, number 2, keep going, and so forth, right? So it'd be useful for us to reference this somehow. So you can say strings, and we can store this file in some file called string.txt. Right, so this command here will say take strings, read out the strings in the BOM binary code, and store it in strings.txt. We're also going to give it another flag here. This .t flag, all this does is it adds a line number to it. Right, so the original printout is this long sequence of strings. If you give it -tx, it'll add a line number to it, showing where in the binary file each of these shows up. So now we can look at strings.txt, and now you've got all the strings as before, and there's a helpful little index showing where in the binary file each of these strings show up. So that's one helpful thing. Another helpful thing is this BOM file, right? This BOM file, if you look at it again, this BOM file, it's this binary code, but this binary code, you can also kind of try to extract the original assembly language representation from it, right? Remember, the sequence of binary code here, it's encoded in assembly language. There are sequences of binary numbers in here that correspond to binary instructions and arguments to those assembly instructions, like registers and memory and so forth. So we can use objdump. So what objdump does is it takes a binary program and it extracts the assembly code back from it. So the -d flag will do that for us. So -d takes a binary file, extracts the assembly. So we can say bomb, and we'll store that in a file called bomb.s. .s indicating that it's an assembly program. Right? We don't have bomb. We don't have the full bomb.c. We can get some assembly instructions out of this in the form of bomb.s stored here. So now we can look at bomb.s. And it's taken the bomb binary and extracted this assembly back out. Right? It does its best to extract out the assembly meaning in it. And in here, there's a bunch of things, right? So not all of it is relevant for cracking this assignment. In fact, very small pieces of it are the useful clues for doing this. But you'll want to kind of casually kind of browse through this, right? So here is a label called main. So probably the program starts here somewhere. And in main is implemented in this way. It seems like here it's calling a function. So we haven't discussed what call q means, but this is an assembly instruction that means, okay, call this function, right? So it'll call this function, and if it comes back out from this function, then it says, okay, phase diffused, right? So this is the structure of bomb.c now reflected in assembly code. So we can go look for where is phase 1, right? So let's go look around. We could also search for it, but here, aha, it's phase 1. So here at this label in the assembly program, here are the assembly instructions that implement phase 1, right? And in phase 1, it seems like, okay, we don't really know what all of this is yet. There's some things we recognize, right? We've already talked about, well, LEA means. The low, oh, we have not actually. There's some instructions that we recognize here, like add, for example. But overall, it seems like it calls this function. It's comparing strings somehow, and that's it, right? So the meaning of this, strictly speaking, is opaque to us for now. But at least at this point, you get an idea of the structure of bomb.s. Okay? Any questions up to this point? Right, so what have we done so far? So far, we've extracted strings that gives us some clues. We've extracted the assembly code from the binary, and it shows us, okay, here is how the bomb program is implemented as assembly instructions. Okay, great. And there's also this other useful file if you want to extract that too. It's just called the symbol table. This also offers some clues as well. And that's something that you may want to reference. Okay, so in the course slides here, right? So far, we've done this. We've extracted the assembly. And as an example, you can also see here is the implementation for phase 1 inside the bomb. And here's an example of how phase 1 is implemented. And so it already gives you some clues on how to make this happen, right? So one critical thing is, okay, explode bomb. This is a call to a function called explode bomb. And probably you'll want to avoid letting this function execute, right? So somehow you'll want to set it up so that this program runs with the input you give it. And whatever it decides, it avoids calling explode bomb. And that's basically the objective of each of these phases, right? You want to let the program run through all of this without triggering this function here. And again, there's some of this that we haven't talked about in class yet, right? So exactly how control flow is done, this is something that we'll talk about on Thursday. Right now, what we're doing is get you set up with the environment for doing programming assignment 4, Bomb Lab. Okay. So another important thing here is we need a way to run the bomb program without just letting it blow up, right? So this doesn't require too much motivation, right? The hidden objective of this assignment is to train you to be accustomed to using something like GDB. So GDB is a debugger. It allows you to run programs, but with a very high level of control. It allows you to step through the program line by line. It allows you to look at what's going on inside programs, right? It's a debugger, right? So if you've used it for Java, for example, the high-level concepts of what a debugger does may be familiar, right? So if you use something like VS Code has a debugger built into it. You could also use it to debug Java programs, right? So the idea is instead of just using a lot of print statements everywhere, you can use a debugger, which effectively allows you to examine the program as it runs, just like using a bunch of printf statements, right? And in fact, if you're accustomed to it, it allows you to debug programs a lot more efficiently. So that's what we'll do now, right? So we'll use GDB to run the bomb, right? Remember, if you just ran the bomb, just like so, and tried to randomly test answers to it, you'll just keep setting off the bomb, and the grade of this bomb will just keep decreasing, right? So instead, we'll do GDB. This runs the GDB program, and we'll run the bomb program inside of GDB. Right, so say GDB bomb. This will start the debugger, and it will debug the bomb program. So now that we're in GDB, it's very helpful. Right? It's a textual interface, so there's just a lot of text here. But it's helpful. It says, OK, for help, type help. So we'll do that. So this gives you a menu, a rather overwhelming menu of all the things I can do, right? So each of these are categories of things that GDB can do. And if you wanted to learn this in your own time, you can go through this and kind of see what kinds of features it has, right? So I'll point you to some helpful things so far, right? So one thing that is useful is take a look at help layout, help. Layout. And once you type help layout, it'll say, OK, here are various options relating to the layout of GDB. So layout in the sense of how information is displayed in GDB. Right, so it suggests, OK, you could use this by doing, say, for example, layout previous, layout next, or you can say, pick one of these layouts down here. Right, so let's try layout next. OK, so in this screen here, if you had access to the entire source code, it would display the source code for bomb program alongside the execution progress. Okay, so that's one layout. Take a look at what else it has, layout next. So here in this view, it's showing assembly of the program alongside the running terminal of the program. Right? So for example, just to make this clear, right? So here it's showing, OK, the progress of the program here. And alongside that, it's showing where in the program it is at. Right? So that's one view. So for example, here it's saying, OK, we're right now in this instruction of assembly code here alongside the execution progress down here. OK, layout next. Let's keep toggling through this. Oops, go back. Somehow quit out of GDB altogether. Right, so here is another split screen mode. It shows the bomb.c alongside the assembly instructions. Some more. And here, this one's showing the register values inside the CPU as it runs through the program alongside source code. And here's another version, but instead of source code, C source code is showing assembly instructions. And this seems to cycle back to the source code view. Okay, so for this assignment, there's a recommendation here. So I recommend that you use either layout ASM, which shows the assembly view, or layout reg to show assembly code and the processor register values side by side. Okay, so a few more hints here. Right? So any questions so far about just like the GDB environment, what even we're looking at so far, and what's the purpose here? Okay. Does this make sense what we're doing? Someone want to summarize why we're using GDB right now at all? Why are we using GDB? What's the point of this? Someone else over there. Good, that's right. Right. So we want to run the program while observing the state of the program. State meaning like the variable values, for example, where we are in the program, what's being stored in the registers, and being able to see all of this will allow us to pick apart the BOM, even though we don't have the BOM source code. Right? We can't go and print F stuff because we don't have the source code. We can't compile the BOM over again and just like print stuff out. Instead, we're given just the binary code, which is opaque to us, and we have GDB and some assembly to kind of figure out what's going on. Very good. Okay, so very good. So let's finally run this, right? So another helpful menu here is help running, which will show you some list of commands relating to running the program, running the BOM program inside GDB. Right? So there's a bunch of these. Not all of them are useful for our purposes, but here is kind of the menu if you wanted to see the full range of things you can do. If we go through our class slides here, it kind of highlights some of the key useful ones here, right? So far we've run GDB BOM, good, we're inside GDB. And one thing you can do is called setting breakpoints. Right? So who's heard of breakpoints before? Very good. So why have you heard of breakpoints? Anyone else? I see one hand. Wants to tell me why, what are breakpoints, or where else we've seen breakpoints before? Over there. Yeah. So there are places in code where you can effectively stop the program. Did you guys use breakpoints in Java programming before? So a lot of nods. Okay, good. So same idea here, right? So instead of using system.out.print everywhere in your Java program, you could say, okay, I want to set a breakpoint at this function, and it will take you into the debugger for Java, from which you can look at the values of variables. Right? So this is more sophisticated than just putting a bunch of printf statements inside your code. So what we're going to do here is we're going to set a breakpoint at explode BOM. Right? So that seems useful. Right? Instead of just like calling explode BOM, we're going to let the program run to the point it says, I'm about to call explode BOM, and it will stop the program there, and we can look around at that point. Right? So I'll say break explode BOM. Right? And tab completion works here. Why does tab completion work? Right? Tab completion works here because GDB also opens up a strings file. Right? It extracts what strings you have in the binary and it knows, okay, explode bomb is a sequence of characters inside the program. And so you can say, I want to set a breakpoint at this function called explode bomb. So now I have this breakpoint set. I can say info breakpoint. So it tells us now that currently GDB has set one breakpoint at a breakpoint called explode bomb, right? And this has an address, right? So this is a location in the assembly program where once it's about to call this assembly program function, explode bomb, it will stop the program. Right? So we can say run. Okay, it runs the program. I can give it a wrong answer just as before, hello with a W. And now it's triggered the breakpoint. It says breakpoint 1 triggered explode bomb, about to call it. What would you like to do? I'm back at the command line now. I can do things. Right. So I can say run, and that will, no. I can say continue. So what happens if I hit continue now? Yeah, so it's paused at explode bomb, and if I say continue now, it's just going to run explode bomb, right? So there you go, boom, it blew up. So how do we avoid causing it to blow up if it's already helping us, helpfully pausing just before calling explode bomb? How do we stop it? Right, so how do we stop it? Right, so one way you can figure that out is we can say help running. And maybe in here, it gives us a clue on how to get GDB to stop a program. And the answer is here, right? So the command is called kill. It will kill the program that's currently being debugged, right? Some of this computer science terminology is very, I don't know, gruesome. So let's demonstrate that, right? So I have info. So breakpoints. I still have the breakpoint set. I can run the program. It will start out over again. I could give it a answer. And it will say, okay, that's not the right answer. The bomb's going to go off. Explode bomb about to take place. And if you see this, you can always just say kill, and it will stop the program and never set off the bomb. Right? So this is super helpful. You can inspect this program as much as you wish, so long as you have a breakpoint set just before explode bomb. You can run the program with wrong inputs, and it will allow you to just like quit out of the program without recording a bomb going off. Sound good? Any questions up to this point? Yeah. Sure. Let's try doing that, right? So I believe there's a command called call, right? You're nodding or no? Unclear? So let's try doing that, right? So we'll run program. It will take us up to the point of explode bomb. And what's the function that we can use here? Call. Sure, right? Or another thing I do know that exists is, remember there's a function called phase diffused, right? So let's try doing that, right? So right now I'm about to trigger explode bomb. I believe there's a function called call, a command called call. And what I'm going to tell it to do is, okay, from this place in the program, right? From this place in the program, right now I'm in assembly where the label is at explode bomb. you've got all this register state up here, right? The RAX register, RCX register, and so forth, right? The CPU register state of the program. Maybe we can say call phase diffused, right? So there's tab completion here. There's these phases, phase 1, phase 2, phase 3, phase 4, phase 5, phase 6. And there is a function called phase diffuse. So instead of going through explode bomb, let's somehow force the program go to phase diffused, right? I don't think call is the right command here. Jump. Okay, so it says phase 1 diffused. Okay, so it jumps to phase 1 diffused. It seems like it's asking for some more input, and now it's allowing us to go forward and call explode bomb. Right? I'm not sure this approach will actually allow you to diffuse the whole bomb. You could keep trying this and see if it allows you to get through it. I'm pretty sure there are safeguards that prevent you from doing this, right? So ultimately, you still need to set up the program state, giving it the correct input, because the later stages, these phase diffuse functions will actually check if you computed some correct result, leading into phase diffused. Otherwise, the bomb will go off anyway, right? But that's a tricky line of thinking, though, right? So you could try all kinds of things, right? Anything that doesn't set off the bomb is fair game here. Okay, any other questions? Yeah. So Control C, let's see. So Control C is for detecting inside if you're running outside of GDB, right? So let's exit GDB now. I'm going to exit GDB. Command is quit. We'll exit GDB. I'm going to run bomb like this, and it's asking for input. And if I hit Control C, yeah, it allows you to control Cox like this. So I guess that's somehow, the question is like, how come here it's detecting Control C, which is a kill signal, but in GDB, it's able to just quit out, right? That's a good question. Ultimately, I think like here, it's actually reading the command line input and detecting Control C, which is itself a kind of character, and detecting that character. And instead of quitting out immediately, it prints out this little message to mess with you. Whereas in GDB, right, everything is running inside the GDB environment. And GDB can just say, well, the user wants to stop the program is stopped. Everything is just unlinked and killed out. Okay. Anything else to see here? All right, so I think we'll leave the demonstration up at this point. Right, there's some more instructions on running and stepping. These are just like the debugger in Java. We'll cover some more of this on Thursday. And in the notes here, there's also some more hints on how to use print commands to inspect the state of the program. But for now, I think what we need to do is we need to talk a little bit more about assembly again. Right, so we'll wrap up the demo here. We'll continue on Thursday, and then we'll go back to just kind of material about assembly language. So any last minute questions before we change gears? Okay, very good. Okay, So last Thursday before spring break, where we left off was we talked about how in assembly, there are different encodings on where memory is addressed, right? So this is the addressing modes inside assembly. And then we had also talked about how in assembly language, there's all kinds of ways of using less powerful instructions to achieve the same effect computation. Right, so we'll do a quick recap of that and then go on to talk about some new material about how instructions are realized inside assembly. So addressing modes, we had a demonstration of addressing modes in the form of addressing modes.c. There's all of these addressing modes here. The working example here is using the move instruction. So the move instruction basically moves data from inside the CPU to memory or within the CPU between registers, right? So there's various valid ways to move data around. You can move constant values into registers or memory. You can move register values into register or memory, or you can read data from the memory back into a register in your CPU. So how come there's no memory to memory here? Who wants to remind us why there's no mem to mem movement here? So maybe first of all, do we understand what's going on this slide? What's the point of this? Yeah. Okay, so the answer to propose is memory has no pipeline to memory. There's no connection from memory to memory. And that's basically right. So the idea here is this move instruction tells the computer to move data around places in the computer. And all the work is being done by the CPU, right? All the work is being done by the CPU, which understands what instructions are. Memory doesn't understand what instructions are. It can't do work. And so there's no way for us to shuffle that data from memory and immediately move it to some other address in memory. All of that has to go through the CPU first. Yeah. So what is IMM as a source? Right? So what is IMM? So IMM is constant. Right? So the constant here would be something like the hexadecimal value of 4 or a decimal value of -147. Right? So this is if in your program you have a hard-coded constant, 4. Right? That's a value, it's not a variable. And when it gets translated into instructions, it's exactly that. 4 gets stored inside this register, which may be a temporary variable, like so. Or this value, -147, gets stored at some pointer, right? So some memory being pointed to by the pointer P, write the value -147 over to memory. And this 147, -147, this is a constant value that gets stored into memory. So that's what immediate means, constant values. Okay, so the next part here is there's various ways that addresses are expressed. Right, so here's kind of the textbook slides that describe that. You can read this to kind of recap what that is. I'm going to go skip a little bit toward the detailed examples I have, which show the various addressing modes in the form of C code and assembly code down below. Right, so this assembly code is what you would get if you compiled the addressing modes.c program and looked at what the assembly code corresponding to each of these functions gets turned into. Right, so the first form is, okay, we have some immediate value, which we just talked about are constant values. and we're going to store it into somewhere in memory. So the C code here is I want to store into this pointer in memory, this address, this value 0xFFF. So this is 16F, which would correspond to a integer value, signed integer value of -1. And that's exactly what the assembly code says, right? So take a constant value of -1 and put it in to memory, where the location in memory is this address pointed to by register RDI. Right? So somehow this argument here gets stored inside register RDI, and the parentheses mean this is an address, dereference that address inside memory, and put this value inside memory at that location. Right? So this is the first form, the most basic form of memory addressing. And then in the next few slides, there's several different variants of this, right? Various variants of this, all corresponding to idioms inside C on how pointers and arrays work. Right? So the first one is this thing called displacement, where now instead of pointer just being a plain pointer, it's the array called pointer, where the name of an array, remember, is essentially just the pointer to the beginning of the array. And so now, instead of putting it inside array element 0, we're going to put it at array element 1. Okay, so we've got memory starting at pointer, and we're going to put it at the first index position of 1. And like before, we're going to store the value of -1. And when we look at what that becomes in assembly, it turns into this, right? So it says, okay, we have some memory location being pointed to by pointer, which gets stored inside the register called RDI. That's a memory location, but instead of putting it directly there, put it at an offset of 8. And we have drawn this picture of, okay, if this is a long data type, 8 would be 8 bytes farther down would be the first position to store a long integer after the array index 0 location. So this is exactly how array indexing with constant indices gets translated into assembly code that the CPU understands, okay, this is what that means. Yeah, question over there. That's right, right? So if this weren't 1, if this were instead 2, this would be 16. Meaning, okay, starting at this memory location pointed to by RDI, go 16 bytes down, array index 2, the location for array index 2, and put -1 over there. Good question, right? So what happens if it's a variable? Right? So if it's a variable, then it's something different, right? So if we set instead as a variable, right? So now instead of being pointed to by some constant index into the array called pointer, this index now is itself a variable called index. That gets translated to a different format, right? So it gets translated into this format where, as before, the location is starting at RDI, but now it has this format here where RSI stores the index. And this argument here in the assembly syntax says, okay, multiply what's stored here by 8, and that's the new offset into the array where this should be stored. Right, so and that's what this note says here. This syntax here means the memory location stored in RDI, and on top of that, add to it 8, so 8 bytes per long integer, And how many long integers in? Well, how many of those are being stored in RSI, and that's the location where you want to store it. So what you asked, what if it's a variable? That's exactly how this gets translated like this. Okay, any questions up to this point? So this is recap, right? Recap of, okay, just moving data around inside memory and the CPU from register to memory, memory to register. This is the way that assembly syntax records where in memory all this is being stored. Right, and you can go look at the assembly code for addressing modes and see that, okay, as you change some things around, right, if you change the data type of what's being stored, correspondingly, the increment for each index changes, right? So far we've been working with long types. And so as you increase the array index, that gets multiplied by 8, meaning that, okay, array index 1 really is going to be 8 bytes farther down. If the data type were integers, that changes things up, and so forth. Right, so what's the takeaway here? Right, the takeaway here is, well, when you change things in the C syntax, that change in the data type is realized, is implemented using different instructions in the assembly and different ways of addressing memory. Right? In a very real sense, the hardware allows you to have these different data types in C. Okay, so the final format here is a mix of the two, right? So we talked about how, okay, you have an array, we have constant index displacement, and also variable index displacement. And what if you had something like this, which is, okay, I have some variable index, and on top of that, I have some constant increment on top of that. Well, okay, the assembly has some way of representing that just as well. So that looks like this. Okay, so that's addressing modes. The next kind of topic we talked about was, okay, then in assembly, there are ways in which complex operations are compiled down into simpler operations that the CPU can do efficiently. Right, so the CPU, because it's doing all of this like addressing modes work, it's very good at calculating things of this format, right? Give you a constant, give you a variable index, multiply that by some increment, and then add to that a constant offset. So very oftentimes it will take programs that look like this and transform it into a format that piggybacks off of that ability to calculate memory very effectively. Right, so the instruction for that is called LEAQ, which is short for load effective address quad word. Right, so Q just specifies the result is going to be a 64-bit value. And the example here is that, okay, I have some multiplication here, and instead of compiling this into an instruction that uses multiplication, it's getting compiled into this instruction here that uses LEAQ. And we had some examples of this in the example code, example programs that we have, where on the left-hand side here, I have two C programs, LEAQ, moladd. One, the LEAQ program is completely about array indexing and getting addresses, right? So here, I have a pointer, I have a variable indexed into the array, and I want this function to return the address of this location. So clearly, this first program here, LEAQ, is all about addresses. And on the bottom here, I have a different program altogether. This program here is all about multiplying and adding values, right? So I have a base, I have an index, give me the value of base plus index times 8 plus 8. Okay, this is just some kind of math operation. And if you look at how both of these programs are compiled into assembly, well, the implementation of the two is exactly the same, right? And the reason for that is the CPU is so good at calculating this instruction here that it will do its best. The compiler will do its best to take instructions of this, take programs of this form and turn it into something that the CPU is very good at. Okay, so this is just kind of an interesting quirk that you'll see inside the assembly as you work on PA4 too. Good. So any questions up to this point? Good. Okay, so that's recap up through LEAQ. Next, we'll talk about how in assembly, there's this tricky thing where if we're doing casts, right? When we cast values from one type to another, the CPU has to keep track of, well, the CPU and the program and the compiler have to keep track of how exactly the data type, the signed and unsigned data type of those numbers are being kept track of inside the program. So here I have two programs now. Both of them are effectively, well, essentially what they're doing is they're taking as input a character, an 8-bit value, and casting them into short 16-bit values. And the difference here is on the left-hand side here, I have unsigned characters being turned into short. So unsigned character UC to unsigned short US. And on the right-hand side here, I have signed characters, so signed characters SC, being turned into signed short SS. Okay. So the semantics of this program are different, right? So if we write the C code here and the C code here, well, we would expect that it should respect our decision on whether the values are signed or unsigned. Right? So on the left-hand side here, I have, okay, unsigned characters being turned into unsigned short. So the value 255 as an unsigned short should be converted into a unsigned character being turned into unsigned short. 255 gets turned into 255. And so a valid way to do that should be, okay, I have 255, and as it's being upcasted to a short data type, it should pad the left side with 0. So this 8-bit value here is the same as this 16-bit value here. If both are unsigned, then this is how 255 is represented in both. Now, on the right-hand side here, the situation is a little bit different, right? So on the right-hand side here, these are signed characters being cast into signed shorts, right? So for signed characters, the biggest value you can store is positive 127. And if you want to turn that into unsigned short, 16 bits, the left-hand side here should be padded with a bunch of zeros. Okay, very good. But if it's a negative value, negative 128, which is represented as this binary value here, 1 followed by a bunch of zeros. This is the most negative value you can store in the signed character type. You want to upcast that to signed shorts. The left-hand side here should be padded with 1s instead. Right, so clearly, right, so the subtle thing that I want to show here is depending on what's the data type, the correct operation in terms of bit by bit that should be taking place is different depending on the data type. Do we see what's the difference here? Right. On the left-hand side here, it seems like a straightforward rule to convert from characters to shorts is to just add zeros. But on the right-hand side here, the correct thing to do to preserve the right semantics depends, right? So it should either pad zeros or it should pad 1s. And in fact, it seems like the number that it pads by should be whatever the leftmost bit here is. Right? So 0 padding zeros in this case, padding ones in this case. So if you compile these two programs into assembly, the way that it's keeping track of this semantics is fundamentally, it's using different assembly instructions to do this. Right? So the keywords here are, furthermore, there are two different kinds of move instructions. One is called move Z, and the other is called move S. So, right, remember so far we have move Q, move W, move, so forth, indicating the different sizes of the moves. And here, another flavor here is, okay, there's moving Z and moving S. Moving Z means pad the left side with zeros all the time. And move S means, depending on what the leading bit is, pad it with that. Pad it with either zeros or ones so that the positive and negative values are maintained. Okay? This makes sense. So what's the point of this? What's the recap of what's going on here? Yeah, over there. Mm-hmm. That's right. Right. So depending on the data type, the right way to extend the values depends on whether it's a signed or unsigned value. And assembly enforces that by using different instructions. Right. So that's kind of the top-down view. We can reverse that viewpoint, right? We can think about it in a different viewpoint, which is the fact that the CPU understands these two different instructions. Right? There's digital electronic circuitry that does these two different operations. This hardware support is what then builds up to our ability inside the C language and Java language to have these different data types. Right? This is the hardware supporting what is possible inside software. The sign extension, for it to be correct, is always the leftmost bit, MSB. Right? So the example here is, if you wanted to make sure 127 is still 127, then the right thing to do, the correct thing to do, is pad it with whatever the MSB is. Zeros meaning positive numbers, 1 meaning it's a negative number. And keep in mind that this is, once again, 2's complement notation. Okay, so that's the subtlety around sign extension. And that is the most interesting parts, right? So the next more interesting thing is there's also the shift operations. And then these two, bitwise operations and arithmetic, these are much less interesting. They're pretty straightforward. Right? So let's talk about shift operations next. Right? And why are we doing this, right? Remember, what's going on here is we're basically going through all the things you can do in C. Right? What are things you can do in C? Well, we can move things around. We can assign values one to the other, right? We can cast data from one type to another. We also have the operators, right? We can shift values, we can AND things together, we can add things together, we can multiply things, we can take the modulus, we can divide. All of these things that you can do in C, the fundamental things that you can do in C, they have analogies in assembly because C is very close to the assembly. What you can do in assembly, C very closely matches that, right? So up through here, we've done moving data around, we've done casting data, and now we're going to round out the rest in terms of operators: add, subtract, shift, multiply, divide, modulo, and so forth. And among those, among that whole cast of characters, okay, well, the one slightly interesting thing is the shift operators, once again, where in the shift operators, there's a very similar kind of trickiness, just like the sign extension that we talked about before, right? So here we have left shift, right? So what happens when you left shift by 1? What is left shifting equivalent to? Yeah, left shifting is just like multiplying by 2, right? If you had 0, 1, binary number 0, 1, you left shift by 1, that becomes 1, 0, and that becomes 2. So shifting left is like multiplying by 2, moving the digits into more and more significant places. And left shifting is pretty straightforward, right? So left shifting, we've established that as you left shift things, the value that comes in from the right should just be 0. The least significant bits should just be 0, so that left shifting means adding, so that left shifting means multiplying by powers of 2. Right? So that's what this program is showing. If you compile these two different programs, one is unsigned, the other is signed, what it's going to do is left shift this input by some of this other variable, and all of these get translated. Both of these programs gets translated to this sequence here. So it looks like left shifting is the same. Now, if you do this for right shifting, and again, we're comparing the unsigned version and the signed version, now the case is slightly different, right? So unsigned versus signed, they get compiled into different assembly programs. And if you compare them in more detail, the difference is there's this instruction called SHRQ, and there's this other one called SARQ. And basically what they're doing is one always pads the MSBs with 0, while the other one preserves the signed number, right? Preserves it's a positive number or a negative number, right? So it also does this sign extension. Okay, so we'll study this in a little bit more detail on Thursday. But basically, so far, we've talked about all the interesting operators in C, right? The rest of the characters are much less interesting, right? So the rest of the characters are like logical not, logical and so forth. Those are pretty straightforward. Okay, all right, so see you on Thursday. Hi. Yeah. Pleasure.
Yeah. I could have run the prompt program. It would just say access the adding set up properly, or
So and we put it. Okay, so quit GDB. So just type quit. How did you move this into iLab?
So I download the file on my desktop and then just drag into the.
Did you
iLab.
unpack it on iLab or did you unpack it on your desktop?
It was like a bar, and then there's a folder in there, so I just zipped
So
out the folder.
you unpacked it here on the laptop,
on the
and then you drag and drop that to. Okay,
Yeah.
so yeah, so that's what happened. If you type ls. Okay, so this just lists the file. Now type ls -la, no space after that. So yeah, ls-la, hit enter. So what this shows is the files and also what are the permissions of each file, right? So in Linux, this is the permissions, and it's saying that bomb, you're allowed to read and write it, but you're not allowed to execute it. Right, so the reason that it's set up to these permissions right now is because you just dragged and dropped. It took on those permissions because that's how your computer is set up to do when you drag and drop. And so to make bomb executable, what you should do is now here type chmod. Yeah, chmod.
Oh.
So chmod means change. What does chmod stand for? Yeah, I actually don't know what it's short for. So the chmod changes permissions. So chmod, you can say, okay, chmod is command space. U, meaning yourself, user.
Like my user on the.
No, just character U.
Oh.
No, like as a single character U. U plus. So U plus means, okay, for you, the user, add the permission X. Yeah, just hit X now. So U plus X means for you, the user, add the permission to run this program as executable. Which program? Okay, space bomb. All right, so now it's going to change your permission as a user so you can execute this bomb. If you hit enter and list LSLA again to see what happened. So now you see that for bomb, there's now an X there, meaning you, the user, can run it as an executable. And you also see that the color has changed, right? So color coding means if it's a program, it's something you can run. So now bomb is executable. Yeah. So the way to prevent this from happening in the first place is if you just move the whole tar file first and then unpack it on iLab instead of unpacking on your computer and moving the whole directory over, you wouldn't have run into this problem.
Okay. And I have another question. So I saw when we did it up here that there's an 8 here. I don't know what does like 8 stand for.
So well, before even looking at this slide, you can go back farther up 2 more slides, which is even or farther up here, right? So to understand why there was an 8 where you asked, the same reason that there's an 8 here. Why is there an 8 there? So what that 8 means is this is the memory, right? The memory is a bunch of bytes represented, well, a bunch of bytes. The bytes are all addressed, right? So we can have an address here, for example. These addresses can have names like PTR. Right, so pointer is a pointer. It stores the address. It points at somewhere in memory. And each of these store 8 bits. Right? And inside this 8 bits, we're storing long types. So this is an array of type long. Right, so this pointer here, it points at a long, which is 64 bits. So that's 8 bits here, 8 bits here, 8 bits here. So overall, it takes 1, 2, 3, 4, 5, 6, 7, 8. It uses up all of these cells in one go to store one long. So here, instead of storing into PTR 0, right? Instead of putting the data in here, we would like to put data into PTR1. The address for that should be all the way down here, right? So the address for this is going to be 0x20, 12, hexadecimal 12 plus 8 hexadecimal 20. And to calculate what this address here is, it's 8 more than whatever PTR is. So that's where you get 8.
Oh, okay.
Yeah. Hi.
I want to clarify what's the bomb lab and like trying to do it incorrectly by just setting things up in GDB and calling the method that like sends the message. Is that all fair game to try and kind of work around like finding the actual string?
Yeah, right. So wait, what are you asking? So
like instead of trying to reverse engineer to find the strings, trying to go into GDB and then like, I don't know if you can even set register values or whatnot, but just like skip around and do what you had done there, but for the other phases as well.
So I think there's at least 2 ways, right? So one is to find what is the correct input. And the other is, as you suggest, like manipulating the register values so that the program gets into a state where the bomb is disassembled. Yeah, that's fair game too.
Oh, okay.
Right, but I feel like actually figuring out what the right solution is the more straightforward way. But I guess if you want to take on the challenge of like hacking the program state so that it registers the bomb as being diffused, I suppose that's doable too.
Yeah, it seems like a fun way.
Yeah.
Probably more.
I think you'll probably discover a bunch of safeguards that they have engineered into the bomb program. Like as you say, right? So what we had tried was we did manage to kind of skip into phase diffused, which I was kind of surprised about.
On the submission site, it did say invalid phase 1 though.
Okay,
So,
well then that means that yeah, so it's not actually registering the right solution.
Yeah.
Yeah.
So it'll be more synchronous.
Yeah.
Okay.
Wait, so you saw bomb 142, the demo I did?
Yeah. It's
Interesting. Let me see.
And also a bunch of other people, I think, heard it.
Oh, okay.
Yeah. 142.
Board. Let's see. Well, that'll refresh. Okay, yeah, see, okay, well, yeah. So yeah, the bomb does have ways to kind of detect tampering. Yeah. Hi.
Hi, when I obtained the bomb from Atlas, I got 3 files here with ID. I just wanted to confirm.
Yeah, so you can double check, open them up. You'll probably see that, make sure that all of them are registered to your net ID.
Okay.
Right, remember there's a README file in there?
Right.
And that's fine. You have 3 different bombs. You could, for example, start with 162 to start learning and find your way around. And so far you have 3 bombs downloaded, all in your name. And in this circumstance, the last one, the 170 one, that would be the one that would be the one that counts. Right, but if you mess that one up too, just get another bomb.
Another bomb.
Mhm.
Right. Okay, perfect.
Hi.
Okay. So first thing is with this bomb in phase 7. When I do GDB bomb, do that and then run my solution. It works, right?
Yeah.
But for phase 7, if I do it's supposed to work. But if I do it again, it didn't work last time.
Okay, all right. I think what probably happened was, well, so now it works, right? So probably what happened was this modification has to synchronize with iLab. So I think you probably hit save here, and you ran the terminal before the files had uploaded. And that's why you ran into a problem. I saw your question on Piazza.
Okay.
Yeah.
And are you free Friday? I have another class, Honors College Farm, is talking about technology in low socioeconomic communities, and I want to try and interview the professor, CS professor, and I'm just asking anyone who's available.
On Friday, what time?
Just any time Friday afternoon.
And what is this event? Or what is the context? Or maybe hold on to this. I'll take your question first, and then I'll come back to you. Oh, okay.